Hello, Hor. In this project, we are going to cover about heart attack detection using ECG signals. Cardiovascular disease is the leading cause of death with 17.9 million deaths annually. The key point is 85% of the cases are preventable with early detection. With key technologies like real-time ECG monitoring, we can continuously track heart activity. And when we combine ECG signals with clinical data, we get much accurate diagnosis. However, current systems have major limitations. They depend heavily on experts, which is time consuming. There is also a risk of human error, especially under pressure. Data is often separated, leading to incomplete insights. And finally, many AI systems are black boxes reducing trust. So there's a clear need for a better intelligent solution. Solution is a hybrid AI-based system. It analyzes ECG signals using deep learning and clinical data using machine learning. We then combine both outputs to generate a simple, accurate result. Importantly, the system also provides explainable doses so clinicians can understand the result. Overall, this enables faster and more reliable decision making. Thank you.
In this slide, we will see the overall system architecture, which is designed as a structural four-stage pipeline for efficient and accurate prediction. In the first stage, both clinical and ECG signals are collected and pre-processed, where normalization and scaling are applied to ensure consistency across inputs. In the model layer, a CNN LSTM network is used to analyze ECG signals by capturing temporal patterns, while a random forest model processes clinical features to estimate risk. The outputs from both models are then combined in the fusion layer using a weighted strategy, allowing the system to leverage the strengths of each model. Finally, the output layer displays the result through an interactive dashboard, along with an AI-based explanation module, improving both interoperability and user understanding. This is the input data used in our system, which consists of both clinical data and ECG signal data. The clinical data includes 13 important features such as patient demographics, vital signs like blood pressure and heart rate, cholesterol levels, symptoms, and medical history. On the other hand, the ECG data is processed as a signal input with a fixed window of 200 data points centered around the R peak to capture one heartbeat cycle. We also apply normalization and pre-processing techniques to ensure consistency and improve the accuracy of the feature extraction for reliable prediction.
In this slide, I will explaining the machine learning model used in your system and how we improve prediction accuracy using a hybrid fusion approach. First, let's talk about the random forest model, which acts as our clinical model. This model is built using an ensemble of around 200 decision trees. Instead of relying on a single decision, it combines multiple trees to produce more accurate and stable prediction. Another major benefit is that it can handle missing or incomplete data effectively, which is very common in the real world healthcare datasets. This makes the model reliable and robust. Next, we have the CNN LSS model, which is designed for analyzing ECG signals. This is a deep learning model that combines two techniques. The CNN are responsible for extracting important spatial features from ECG waveforms such as shapes and patterns. Using the combination, the model can effectively detect QRS, complex changes, and T wave abnormalities, which are key indicators of heart problems. Finally, it outputs the probability of abnormality in the ECG signal. Now, instead of depending on just one model, we use a hybrid fusion but logic to combine both models. We apply a weighted combination where 60% importance is given to a clinical data and 40% to ECG data, since clinical factors often have high long-term significance. Based on the combined score, we classify patients into three categories: high risk, medium risk, low risk. The hybrid approach helps us improve overall prediction accuracy and reduce false alarms and ensure that critical cases are not missed.
Our system also includes explainable AI, which acts as a virtual cardiologist. Instead of giving only a prediction, it explains the reason behind the result in simple language, making the system transparent and trustworthy. Next, in the result, the ECG signal is analyzed using CNN LSTM model, while clinical data is processed using a random forest model. Both outputs are combined using our hybrid formula, where 40% weight is given to ECG and 60% to clinical data. Based on this, the system classifies the patient into low, medium, or high risk improving overall accuracy and reliability. In conclusion, our project successfully integrated ECG analysis, clinical prediction, and explainable AI into one system. In future, this can be extended to real-time monitoring using wearable devices and can be developed into a complete clinical decision support system. Thank you.